Okay, digging back into the deep recesses of old calculus tests. This one comes from 1984. I actually couldn't even find a key for it online. I didn't look that hard, but I classify it as type 7. Again, it's a related rates problem. 1984. It's a long time ago. It's also a good book you ought to read. The volume of a cone is increasing. So we have a cone. I'll sketch a little cone right here. Cone. A cone has a radius and a height. So there's the cone. The volume of the cone is increasing at a rate of 28 pi cubic inches per second. So the rate of change of volume is 28 pi. At the instant when the radius on the cone is 3 inches, the volume is 12 pi cubic inches. So they're saying there's a snapshot moment, so it's kind of like our when statement. When the radius is 3, the volume is 12 pi. And the radius is increasing at a rate of ½ an inch per second. So that's our given. Given the radius is increasing at ½ an inch per second. Now, in this problem here, they actually have not provided the equation for the volume of a cone. I think in modern calculus tests or at the front of the packet, oftentimes they'll give you these general geometry formulas, but the formula for the volume of a cone is 1/3 pi r squared h. I think nowadays they may even provide it within the context of the problem, but that's the relationship between volume and radius. It also depends on the height. So this when statement, they give us a radius and they give us a volume, so we can deduce the height based off of that information. What is the height of the cone? So we'll very quickly crunch those numbers to figure out what the height is. 12 pi equals 1/3 of pi times 9 times h. And we find out that the cone at our snapshot moment is a height of 4 inches. Okay? So we used existing information to find new information. Okay, part A asks us, at the instant when the radius of the cone is 3 inches, what is the rate of change of the area of the base? So we're trying to relate radius and area. And for a cone, the area of a base is a circle. So the relationship that we're looking at is the area of a circle. It's going to be relating the area to the radius. And they're asking what is the rate of change of the area of the base, so what is the value of dA dt? So we differentiate with respect to time, and we get 2 pi r dr dt for the right-hand side, and we have all of the information we need to evaluate this. So when r equals 3, the area is increasing. If we stick in the numbers, we get 2 times pi times a radius of 3 times a rate of change of radius of 1/2 inches squared per second. And if you do some simplifying here, the 2 and the 1/2 cancel each other out, and the area is increasing 3 pi inches squared per second. The unit of area is square area, so that's why it's inches squared. All right, so part A focused on just the area of the base of the cone. In part B, we're starting to actually get into the height, so we're going to need to use our volume equation. So let's set that aside. Part B. At the instant when the radius is 3 inches, what is the rate of change of the height? So we're trying to find dH dt when r equals 3 given, and we're given a couple rates. We're given dV dt is 28 pi, and we're given dr dt is 1/2. Also, we've established that when the radius is 3, volume is 12 pi, and h is 4. So that's all the information that we established prior to executing Part A. And the equation that relates volume to radius and height for the cone, as also written above, is 1/3 pi r squared h. So when we differentiate this with respect to time, we're going to have a dV dt, a dr dt, and also the dH dt. So this should work for finding dH dt. The common mistake here that I've seen is that oftentimes people fail to notice this is a product and therefore needs the use of the product rule. So when we differentiate, treat this as a product, the first derivative times the second plus the second derivative times the first. And that's our derivative with respect to time, taking account for the fact that we have a product. And from here, it's a plug and chug of numbers.
Pretty much everywhere, it's gonna be hot. Try that?
Then I don't need a jacket. Thanks, Arthur.
Okay, then let's start plugging in all the things that we know. 28 pi is our dV dt. 2/3 pi radius dr dt times height plus our unknown was dH dt times 1/3 pi radius squared. And then all we have to do is the arithmetic or the algebra of solving for this variable. So the 3's cancel each other, the 2's cancel each other, leaving behind 4 pi in that first term. And then 1/3 of 9 is 3 pi. And then subtract 4 pi to the left, 24 pi, and divide 3 pi to the left, divide by 3 pi, is equal to dH dt. Pi's cancel. When r equals 3 inches, the height is increasing 8 inches per second.
On to part C. At the instant when the radius of the cone is 3 inches, so we're still dealing with the same snapshot moment, so r equals 3, h equals 4, and v was 28 pi. So at that moment, what is the instantaneous rate of change of the area with respect to height?
dV is 12 pi.
12 pi. Sorry. Thank you. 12 pi. Part C is asking us to find dA dH, the rate of change of area with respect to height. Now, there is multiple approaches to this, and this is not a super intuitive question And I think it is probably why you find a question like this back in 1984. I think the tests were harder back in the day. But check this out. dAdh is the same thing as dAdt divided by dH dt, right? Because the dt's would cancel. So that relationship there is comparing these two in a way that is very fluid because we have found dAdt in part A, and our result in part A was, I forget, 3 pi? 3 pi?
Yeah.
And dH dt we found in part B,
8.
which was 8. And there's our answer.
Oh my gosh.
Okay? It's a pretty big creative leap to go from here to here. But the alternative scenario isn't any easier. We have a relationship of A equals pi r squared. And if we were to take the derivative of this with respect to height, dA dH, we would get 2 pi r dr dH. We're taking the derivative with respect to height. So that's why there's a dr dH at the end. And we arrive at the same scenario where I don't know what dr dH is, but I could write it as dr dt over dH dt. And then that gives me the same value if we plug in numbers there. So 2 times pi times 3 times 1/2 over 8. And we would get the same value of 3 pi over 8. Okay? Now, please keep in mind that on FRQs, like if your goal is to get a passing score on the AP test, a 3 or above, if you're able to get like 4 or 5 points on an FRQ, that's pretty good. And I think you would get that out of part A and B. Okay? Part C nabs you the last couple points of this FRQ. Suitably so, it's a little more challenging. So, 2 approaches, not obvious. Be sure to comment, like, subscribe, mash that button, smash that like button, send money to my Bitcoin wallet, hit the bell for notifications, follow all of my students on Instagram and their vlogs and all of that jazz.